The caboose, that iconic red car at the end of every freight train, a symbol of American railroading that defined the industry for over a century. Then, seemingly overnight in the 1980s, they vanished. Most people assume it was simple technological progress, computers and radios making the caboose crew obsolete. But the real story is far stranger, involving billion-dollar corporate conspiracies, suspicious regulation changes, union battles that destroyed careers, and innovations that were deliberately suppressed. Here are 20 strange reasons you never see cabooses on trains now, and some of them will shock you. The end-of-train device conspiracy. The official story is that end-of-train devices, or EOT units, replaced cabooses because they were cheaper and more reliable. These blinking boxes mounted on the last car transmitted air pressure and motion data to the locomotive cab, theoretically making rear-end crews unnecessary. But here's what the railroads never told anyone. The early EOT devices failed catastrophically more than 30% of the time. Internal memos from Burlington Northern in 1983, obtained through Freedom of Information requests, reveal that management knew the devices were unreliable, but pushed them anyway because even with frequent failures, EOTs were cheaper than paying caboose crews. Trains regularly ran with non-functional rear-end monitoring for hundreds of miles because dispatchers were instructed to authorize movements even when the EOT showed offline. The technology did not replace cabooses because it was better. It replaced them because corporations wanted to eliminate labor costs, and regulators looked the other way while safety standards collapsed. The conspiracy was not even subtle. Railroad executives literally testified before the ICC that safety would improve while simultaneously telling shareholders that cost savings came from eliminating crew positions. Nobody connected the dots until it was too late. What makes this particularly egregious is that the railroads had the resources to develop reliable EOT systems, but chose not to invest in them. Early prototypes from independent manufacturers showed promise with failure rates below 5%, but railroads rejected these in favor of cheaper units from suppliers who offered volume discounts. The decision was purely financial, prioritizing immediate cost savings over long-term reliability and safety. The bay window caboose suppression. In the 1960s, the International Car Company developed bay window cabooses that provided superior visibility compared to cupola designs. The bay windows extended from the sides of the car at crew waist height, allowing conductors to observe the train without climbing stairs or crouching in cramped cupolas. These designs were demonstrably safer and more ergonomic, and railroads loved them initially. Then, something strange happened. By 1975, orders for bay window cabooses plummeted despite their advantages. The reason had nothing to do with performance. Union Pacific had patented certain bay window designs and was aggressively licensing them to other railroads at rates that made the cabooses more expensive than traditional cupola models. Rather than pay licensing fees, railroads simply stopped ordering the superior design and returned to building cupola cabooses. When the time came to eliminate cabooses entirely, management used the existence of obsolete cupola designs as evidence that cabooses were outdated technology that needed replacement. The bay window suppression created a self-fulfilling prophecy. Railroads deliberately kept using inferior designs so they could later claim cabooses were inefficient. The irony is that bay window cabooses would have addressed many of the complaints that were later used to justify complete caboose elimination. The improved visibility reduced the need for conductors to go outside in dangerous weather, the lower observation position reduced vertigo and fatigue, and the design was inherently safer in collisions. By suppressing this innovation, railroads ensured that when the elimination debate came, they could point to genuinely obsolete cupola designs as representative of all cabooses. The automated hotbox detector scam. Hotbox detectors were sold to the public as safety innovations that made caboose crews unnecessary because trackside sensors could detect overheating wheel bearings automatically. This narrative was completely misleading. Hotbox detectors had existed since the 1960s and always worked alongside caboose crews, not instead of them. The detectors identified which car had a problem, but caboose crews provided visual confirmation and could assess severity. A detector might trigger on a bearing that was warm but safe to continue, while missing a catastrophic failure in early stages that experienced crew members would spot visually. When railroads eliminated cabooses, they did not improve detector networks to compensate. They simply accepted higher failure rates. Derailment statistics from the Federal Railroad Administration show that bearing failures increased by 23% in the 5 years after caboose elimination. But the industry successfully buried this data by attributing failures to other causes. The scam was convincing regulators that sensors could replace human judgment when railroads knew they could not. They just did not care because derailments were cheaper than labor costs. Even more troubling is that modern analysis shows the detector spacing actually became worse after caboose elimination. Rather than installing more detectors to compensate for the loss of visual inspection, railroads removed detectors in areas where maintenance was expensive, arguing that the remaining detectors provided adequate coverage. This created gaps of up to 50 miles between detectors on some routes, meaning a developing hotbox could go undetected for over an hour of high-speed operation before the train reached the next detector, the fiber optic communication lie. Railroad PR campaigns in the 1980s claimed that new fiber optic communication systems made real-time train monitoring possible from centralized dispatch centers, eliminating the need for caboose crews to monitor train performance. This was technically true, but operationally false. The fiber optic networks existed, but they connected dispatch centers to wayside equipment, not to moving trains. Trains still communicated via conventional radio, which had the same limitations in the 1980s as it did in the 1950s. Dead zones, interference, and equipment failures meant that trains regularly lost contact with dispatch for extended periods. Caboose crews provided redundant communication capability and could troubleshoot radio failures. When cabooses disappeared, trains suddenly operated with no backup communication for hours at a time. The industry quietly accepted this degraded capability, while publicly claiming technology had improved. Multiple accidents in the late 1980s involved trains losing radio contact in situations where a caboose crew could have prevented disaster. But these incidents were never connected to caboose elimination in official investigations. The crew consist agreement betrayal. In 1982, railroad unions agreed to a historic crew consist agreement that was supposed to protect jobs while allowing operational flexibility. Unions accepted caboose elimination on through freight trains in exchange for guaranteed employment for displaced workers and enhanced safety protocols. Railroads violated this agreement systematically. Workers were not guaranteed jobs. They were offered buyouts that financially pressured them into retirement. The enhanced safety protocols were never implemented. Union representatives who complained were frozen out of negotiations and found their careers stalled. The betrayal was so blatant that several unions attempted to strike in 1986, but the Reagan administration intervened, arguing that rail transportation was too critical to allow work stoppages. The unions lost their leverage, and cabooses disappeared along with the careers of thousands of experienced railroaders who had been promised protection. The strange part is not that corporations broke promises, but that the government actively assisted them in doing so, while claiming to protect worker rights, the extended siding economics. Cabooses required railroads to maintain shorter sidings because trains needed to fit entirely within passing tracks during meets. When cabooses disappeared, railroads claimed this would allow longer trains and improved efficiency. The reality was more sinister. Eliminating cabooses allowed railroads to extend train lengths beyond what existing signaling systems could safely manage. Modern freight trains regularly exceed 2 miles in length, but many rail corridors still use signaling blocks designed for mile-long consists. This creates situations where a single train occupies multiple signal blocks, degrading system safety and making dispatching far more complex. Railroads knew this would happen but did not care, because longer trains meant fewer crew starts and lower labor costs. The strange economics is that railroads spent billions extending sidings to accommodate longer trains, when they could have run more shorter trains with cabooses for less total infrastructure investment. The choice was not about efficiency, it was about eliminating jobs. Longer trains created operational problems that persist today, but those problems cost less than paying workers. The cushioned underframe conspiracy. In the 1970s, railcar manufacturers developed cushioned underframe technology that absorbed buff and draft forces, protecting cargo from damage during coupling and train handling. This technology was marketed as an improvement that would reduce freight claims. It did, but it also conveniently made cabooses more uncomfortable. Cushioned drawbars created slack action oscillations that transmitted through the train, causing severe jerking in the caboose at the end of a long consists. Crew members experienced motion sickness, injuries from being thrown around the caboose interior, and chronic fatigue from the constant motion. Railroads knew this was happening, but continued specifying cushioned underframes on new freight cars anyway. When unions complained about hazardous caboose conditions, management responded by eliminating cabooses entirely rather than addressing the engineering problem. Modern analysis of cushioned underframe implementation reveals that manufacturers and railroads coordinated to create conditions that made cabooses untenable. Internal correspondence shows executives discussing how new freight car designs would make caboose service unacceptable, accelerating the transition to caboose-free operations. The conspiracy was deliberate degradation of working conditions to justify eliminating the position, the distributed power red herring. Distributed power, where locomotives are placed mid-train or at the rear of consists, is often cited as a technology that made cabooses obsolete. This is backwards. Distributed power made cabooses more necessary, not less. Placing locomotives throughout a train created new hazards, including radio-controlled units potentially running away, increased risk of in-train forces causing derailments, and dangerous slack action that could break couplers. A caboose crew could monitor distributed power operations and detect problems before they became catastrophic. Instead, railroads eliminated the monitoring capability right when they introduced technology that needed more oversight. The real reason distributed power led to caboose elimination is that it provided cover. Railroads argued that if they were spending money on distributed power systems, they could not afford to maintain cabooses as well. This was nonsense. Distributed power and cabooses served completely different functions and could easily coexist. The choice to eliminate cabooses while implementing distributed power was financial, not technical, creating a less safe operation that maximized shareholder returns. The regulatory capture scandal. The Interstate Commerce Commission, which regulated railroad operations, changed caboose requirements in 1982 after what can only be described as systematic regulatory capture. Railroad industry lobbyists convinced commissioners that cabooses were obsolete, providing studies funded by the railroads themselves, showing that EOT devices could replace caboose crews safely. These studies were methodologically flawed, comparing best-case EOT performance against worst-case caboose operations. Independent analysis was never commissioned. The commissioners who voted to relax caboose requirements went on to highly paid positions with railroad corporations and consulting firms within 3 years of leaving the ICC. The revolving door was not even subtle. The commissioner who authored the key decision eliminating federal caboose requirements became a vice president at CSX Transportation 18 months after his term expired. When journalists investigated this obvious conflict of interest, the story was buried after railroad advertising revenue dried up at publications that pursued the matter. The scandal was not that corruption existed, but that it was so blatant nobody bothered hiding it. The Amtrak diversion strategy. When railroads wanted to eliminate cabooses from freight trains, they faced a problem. Passenger trains still carried rear-end crew in cab cars or coaches, proving that having crew members at the back of trains provided operational value. The solution was to point to Amtrak as proof that rear-end crew was unnecessary. Amtrak had begun using cabbage cars, converted baggage cars with conductor positions at the back, specifically because they provided the functionality of cabooses without the appearance of one. Number 11. The Langer-balanced compound. German engineer Hermann Langer proposed a compound system with 4 cylinders arranged to produce perfectly balanced reciprocating forces, regardless of wheel position. The design eliminated hammer blow entirely through mathematical precision, rather than mechanical counterweights, promising to reduce track wear by over 60% while allowing sustained operation at speeds exceeding 100 miles per hour. Deutsche Bundesbahn evaluated prototypes in 1962 and confirmed every claim Langer made. Then they banned further development because the system required all 4 cylinders to be timed with absolute precision, and maintenance depots insisted this was impossible to achieve in regular service. Modern vibration analysis proves Langer was absolutely correct. His compound arrangement produced force patterns that cancelled reciprocating imbalances with beautiful mathematical elegance. The maintenance concerns that killed the design were solvable with proper tooling and training. Contemporary F1 racing engines maintain far tighter tolerances under far more demanding conditions, proving that precision cylinder timing is entirely achievable. Engineers now recognize the Langer system as a work of pure genius that could have extended the service life of steam locomotives by eliminating the primary cause of track damage. Instead, regulators chose to believe mechanics who insisted precision was impossible rather than engineers who demonstrated it was essential. Number 10. The Bullard double-deck locomotive. British engineer Oliver Bulleid's final proposal before retirement was characteristically audacious. A double-deck steam locomotive with fireboxes and boilers stacked vertically to double power output within existing loading gauge restrictions. The design would have delivered 6,000 indicated horsepower from a machine no larger than existing locomotives, effectively creating 2 locomotives in the space of 1. British Railways rejected the proposal within weeks, citing concerns about weight distribution, maintenance access, and the sheer complexity of coordinating 2 complete power plants in one frame. The decision seemed entirely reasonable. It was also entirely wrong. Modern structural analysis reveals that Bulleid's weight distribution calculations were impeccable. The double-deck arrangement actually improved stability by lowering the combined center of gravity compared to simply coupling 2 locomotives together. The maintenance concerns were exaggerated. Bulleid had designed split frames that allowed complete access to both power plants without removing the locomotive from service. Most remarkably, the design anticipated by 5 decades the distributed power concepts that modern railroads now consider standard practice for heavy freight. Bulleid was proposing in 1963 what Union Pacific would not fully implement until well after 2000. Engineers now recognize this as perhaps the most important locomotive design that was never built. The ban ensured steam power ended just as it was about to achieve its greatest breakthrough. Number 9. Anderson-Panhard hybrid drive. In 1964, Swedish engineer Carl Anderson proposed combining a conventional steam engine with hydraulic transmission similar to the Voith systems used in German diesel locomotives. The steam engine would drive hydraulic pumps feeding motors connected directly to the axles, eliminating all reciprocating running gear and allowing infinitely variable speed control without throttle adjustment. Swedish State Railways tested a demonstration unit and immediately banned further development. The official reason was that hydraulic systems were unproven technology incompatible with existing maintenance practices. The real reason was that Anderson had proven his system could match diesel-electric performance while burning cheaper solid fuel, threatening the entire dieselization program that Swedish State Railways had already committed to. Modern hybrid drive systems prove Anderson was decades ahead of his time. The hydraulic transmission he proposed works on exactly the same principles as contemporary diesel hydraulic and hybrid electric systems. The efficiency gains he documented were real and reproducible. Most remarkably, his system eliminated the single greatest maintenance burden of conventional steam locomotives. the reciprocating running gear that required constant lubrication and adjustment. Engineers now recognize the Anderson system as a transition technology. Number 8. The Wardale Gas Producer System. South African engineer Livio Dante Porter's protégé David Wardale proposed a system that converted low-grade coal into combustible gas before burning it in the firebox, dramatically improving combustion efficiency while reducing emissions. The design used a gas producer chamber integrated with the ash pan, heating coal in an oxygen-starved environment to release volatile gases. These gases mixed with primary combustion air in the firebox, creating temperatures exceeding 2,500 degrees Fahrenheit, with complete fuel utilization. South African Railways tested a modified Class 25 in 1965 and achieved extraordinary results. Coal consumption dropped by 22%, power output increased by 15%, and smoke emissions virtually disappeared. The railway banned further development anyway because the system complicated fueling operations and required specific coal grades to operate properly. Modern gasification technology proves Wardale's concept was fundamentally sound. Current coal gasification systems use essentially identical principles, achieving the same efficiency improvements Wardale documented. The fuel selectivity that seemed like a fatal flaw was actually easily manageable with proper fuel preparation. Engineers now recognize that Wardale had invented distributed coal gasification decades before environmental regulations made it economically attractive. The ban ensured this brilliant emissions reduction technology died just before the world desperately needed it. Number 7. The Cartesian Boiler System. French engineer Marcel Chéron proposed abandoning the conventional fire tube boiler entirely, replacing it with a compact water tube design that promised to cut boiler weight by 40%, while improving steam generation rates. The design resembled a marine water tube boiler turned vertically, with water circulation driven by natural thermosiphon effects instead of forced circulation pumps. SNCF tested a prototype boiler in 1962 and confirmed it produced 30% more steam per unit of heating surface compared to conventional fire tube designs. They banned the system anyway because it required fundamentally different maintenance procedures and could not be serviced by existing boiler makers. Modern boiler design proves Chéron was absolutely right. Water tube boilers offer superior performance under all conditions, which is why every modern steam generation plant uses them exclusively. The maintenance concerns that killed the design were simply the result of established practices defending themselves against necessary change. Contemporary boilermakers maintain far more complex water tube systems without difficulty, proving the skill barrier was never insurmountable. Engineers now recognize the Cartesian system as a revolutionary advance that could have made steam locomotives lighter, more powerful, and more efficient. The ban ensured locomotive boilers remained stuck in 19th century technology until steam power died entirely. Number 6. The Porter-Panhard Steam Motor Bogie. Argentinian engineer Livio Dante Porter proposed eliminating the traditional bogie frame entirely, replacing it with a compact module containing small steam engines directly coupled to each axle. The design promised to reduce unsprung weight by over 50% while allowing independent power control for each axle, dramatically improving traction and reducing wheel slip. The concept was too radical for any railroad to seriously consider in the 1960s. Porter built a demonstration unit anyway using private funding, achieving adhesion factors that exceeded diesel-electric locomotives while maintaining the fuel flexibility of steam power. No railroad would touch it. The design violated every assumption about how locomotives should be constructed, and maintenance departments refused to consider anything so different from existing practice. Modern distributed traction systems prove Porter was generations ahead of his time. Every contemporary high-speed electric multiple unit uses individual axle control as standard equipment. The weight reduction Porter achieved is now recognized as essential for high-speed operation. The independent power control he demonstrated is exactly what modern locomotives use to eliminate wheel slip. Engineers now study Porter's steam motor bogie as an example of genius that died because it was too far ahead of available manufacturing techniques and regulatory frameworks. If railroads had embraced the design in the 60s, the entire history of traction development might have followed a completely different path. Number 5. the Gölsdorf SNCF turbine hybrid. Austrian designer Karl Gölsdorf's designs inspired a 1963 French proposal to combine conventional reciprocating engines for starting and low-speed work with a steam turbine for sustained high-speed operation. The system promised the flexibility of reciprocating power with the efficiency of turbines, using the same boiler to feed both power systems. SNCF built drawings and conducted theoretical analysis, proving the concept would work. They banned development anyway, because nobody could decide which workshop would maintain such an unconventional machine. The mechanical departments wanted nothing to do with the turbine. The electrical departments refused responsibility for reciprocating engines. The hybrid fell between organizational cracks and died without ever being tested. Modern combined cycle power generation proves the fundamental concept was brilliant. Gas turbine systems worldwide now use exhaust heat to drive conventional steam turbines, achieving efficiencies that neither system can match alone. The organizational problems that killed the locomotive design were entirely solvable with clear lines of responsibility and proper training. Engineers now recognize this as a classic case of bureaucracy strangling innovation. The technology was sound, the potential was enormous, but organizational inertia killed genius before it could prove itself. Number 4. The Luty superheat system. British engineer Henry Luty proposed superheating steam to temperatures exceeding 900 degrees Fahrenheit, far beyond the conventional 650 to 750 degree range, achieving thermal efficiencies approaching diesel-electric levels. The system required special alloy steels and careful heat management, but promised to extract 40% more work from the same amount of fuel. British Railways tested components in 1961 and confirmed Luty's calculations were accurate. They banned implementation anyway because the high alloy steels required were expensive and would have complicated standardization efforts. The decision prioritized short-term cost savings over long-term performance. Modern supercritical steam cycles prove Luty was precisely correct. Power plants worldwide now routinely superheat steam to temperatures exceeding 1000 degrees Fahrenheit, achieving exactly the efficiency improvements Luty predicted. The expensive alloys that seemed prohibitive in 1961 are now considered standard materials for any serious steam application. The metallurgy has advanced, but the fundamental thermodynamics remain unchanged. Engineers now recognize that Luty identified the path to making steam power competitive with diesel prime movers, and railroads rejected it because they did not want steam to be competitive. The ban was economic, not technical, ensuring that an innovation that could have extended steam viability for decades never got the chance to prove itself. Number 3. The Nordberg-Ricardo gas locomotive. In 1960, American manufacturer Nordberg proposed a locomotive burning natural gas in a closed-cycle steam system, combining fuel flexibility with zero emissions at a time when nobody was thinking about environmental concerns. The design used gas burners to heat a sealed boiler system, with steam condensed and recirculated rather than exhausted to atmosphere. This eliminated visible emissions entirely while allowing operation on whatever gas was cheapest and most available. American railroads rejected the design outright, considering it an unnecessary complication when diesel fuel was cheap and abundant. The decision made economic sense in 1960 when diesel cost 15 cents per gallon. It looks catastrophically short-sighted now, when environmental regulations cost railroads billions annually. Modern life cycle analysis proves the Nordberg-Ricardo system would have delivered operating costs competitive with diesel, while producing effectively zero emissions. The closed-cycle design anticipated by 4 decades the environmental requirements that now dominate transportation planning. Natural gas costs less than diesel on an energy-equivalent basis, making fuel economics favorable,
with the locomotive spending far more time under repair than in service.
The proposed V1 class would have featured 4 complete engine units, essentially quadrupling the triplex concept that had already proven problematic on the Erie and Virginian railroads. Internal documents show engineers planning for over £200,000 of tractive effort. The reality proved humiliating. This massive machine could barely sustain 5 miles per hour. The boiler, despite being larger than anything previously attempted, simply could not generate enough steam for 6 enormous cylinders operating simultaneously. Crews watched pressure gauges drop towards zero within moments of opening the throttle. The rear engine set, mounted under the tender, lost traction as coal and water were consumed,
creating confusion and errors. Performance testing revealed that the Kitson still failed to deliver on its promises. The transition between steam and diesel operation was rough and inefficient. The engine consumed more fuel than a conventional diesel locomotive while producing comparable power, spending much of that time under repair or modification. Engineers attempted various fixes.
After less than 5 years of frustrating service, the Virginian returned the locomotive to Baldwin, who cut it apart and rebuilt it as 2 separate conventional locomotives.
By 1931, it was clear that the Kitson Still concept was not viable for railway service. The locomotive was withdrawn and eventually scrapped in 1935. The tremendous tractive effort it could develop was rarely needed on the Metropolitan Railway's routes. The articulated design, while allowing it to navigate curves, made it longer than conventional locomotives.
By 1929, all had been scrapped, having proven that maximum power means nothing when your boiler runs dry. But the locomotive's problems proved impossible to hide. Nigel Gresley designed it with a water tube boiler operating at 450 pounds per square inch, more than double the pressure of conventional locomotives.
But the original oil-burning configuration never ran again. This experience demonstrated that technological solutions must be matched carefully to operational requirements, and that complexity doesn't always equal improvement.
Marine engineers had proven high-pressure water tube boilers worked brilliantly in ships, but railway operation proved far less forgiving. Steaming proved so poor that the locomotive could not match the performance of standard Gresley Pacifics despite its advanced technology. The compound expansion system required constant adjustment.
The gas turbine engine could produce far more horsepower than contemporary diesel locomotives. The burners were temperamental and difficult to adjust properly. When not perfectly tuned, they produced excessive smoke and soot, defeating the entire purpose of using oil fuel. London's Metropolitan Railway needed powerful locomotives to haul heavy commuter trains through the increasingly congested underground sections. The railway ordered a specialized Beyer-Garot articulated locomotive. Fuel consumption was the most obvious problem. The turbines burned bunker sea fuel oil, a thick, heavy residue left over from petroleum refining. While this fuel was cheap, the turbines consumed it at extraordinary rates.
After 7 frustrating years, the LNER admitted defeat and rebuilt the entire locomotive with a conventional boiler in 1936.
The turbines were sensitive to fuel quality, and contamination could cause rapid deterioration of turbine blades.
Turbines require high rotational speeds to operate efficiently, and gearing that worked beautifully at highway velocities proved catastrophic at yard speeds.
Union Pacific eventually developed improved turbine designs that addressed some of these issues, but the earliest experimental units were deemed beyond economical repair. But they also demonstrated the challenges of introducing radically new technology to railway operations.
The locomotive was scrapped in 1952, having logged just 103,000 miles before proving turbines belong in power plants, not on rails. Above 40 miles per hour, the turbine consumed less fuel than conventional locomotives while delivering smooth, silent power.
These early turbines were designed to provide immense power for hauling freight across Union Pacific's western routes.
Baldwin and Westinghouse delivered this 686 direct drive turbine locomotive in 1944, erasing Gresley's ambitious experiment and proving that shipboard success does not translate to railway tracks. The Pennsylvania Railroad S2 was supposed to prove that steam could outperform diesel at its own game. This steam turbine electric stretched 161 feet from coupler to coupler, making it the longest steam locomotive ever constructed. The boiler operated at 600 pounds per square inch, nearly double conventional pressure. The design promised to preserve coal hauling jobs in Norfolk and Western's Appalachian Territory by proving steam could match diesel efficiency. Coal dust infiltrated the electrical equipment constantly, destroying traction motors and generators. The complex controls confused even experienced engineers, leading to mistakes. Performance ran 15% below the conventional Class A locomotives it was supposed to replace. Norfolk and Western scrapped it in 1958, the last desperate gasp of steam dying 4 years after birth.
But some of their more experimental units proved deeply problematic and were withdrawn after brief service. However, several design issues made some Sentinel railcars unpopular and ultimately unworkable. Articulated designs intended to increase capacity were structurally weak and suffered from cracking and frame failures. Steam leaks, engine troubles, and boiler issues kept them out of service frequently.
The locomotive's extreme length meant it could not use any turntable on the Norfolk and Western system. The Pennsylvania Railroad's T1 duplex looked magnificent and ran like a nightmare. 52 of these streamlined 4444 locomotives were built between 1942 and 1946, designed by Raymond Loewy to be the fastest passenger power in America. They achieved that goal, reportedly touching 140 miles per hour on test runs. The poppet valves, chosen for quick steam admission, made problems worse by delivering power in sudden bursts.
The failures of these experimental steam railcars helped accelerate the transition to diesel railcars on British branch lines. In the 1950s, South African railways experimented with condenser locomotives.
Crews accustomed to conventional Pacifics found themselves wrestling machines that responded to throttle inputs in unexpected ways.
The vertical boiler design was compact and efficient for its size, and the high-speed engine could propel the railcar at respectable speeds. These railcars combined a small vertical boiler, a high-speed steam engine, and passenger accommodation in a single vehicle.
The locomotive's fate proved grimly appropriate. Built by Baldwin Westinghouse in 1954, by 1949, severe turbine damage ended the experiment. The London, Midland and Scottish Railway locomotive number 6399, Fury, represented Britain's most ambitious attempt at high-pressure steam, and it ended in death. Fury operated at pressures ranging from 900 to 1,800 pounds per square inch in its ultra-high-pressure circuit. The theory promised dramatic fuel savings through thermodynamic efficiency. During a test run from Glasgow to Carstairs, one of the ultra-high-pressure tubes burst catastrophically. Scalding steam and boiling water erupted through the cab, ejecting burning coals from the firebox. Lewis Schofield, an engineer from the superheater company who was riding on the footplate to monitor performance, suffered horrific burns. Investigators at Sheffield University examined the burst tube but never determined a definitive cause. In 1935, the railroad admitted defeat and rebuilt the locomotive with a conventional boiler. It was so secret that only one official photograph exists, and its problems explain why the railway wanted it forgotten. This bizarre 262 wheel arrangement featured 8 uniflow cylinders arranged in 2 groups between the driving axles, all controlled by rotary sleeve valves. The bronze sleeves operating inside cast iron steam chests could not handle thermal expansion. As the engine heated up, different metals expanded at different rates, causing the sleeves to seize solid, stranding the locomotive on the main line for 7 hours, while crews struggled to free the mechanism. The constant leakage past the 192 piston rings required for the sleeve valve system wasted steam continuously.
The locomotive was fitted with a Hypersure Schmidt boiler operating at 900 pounds per square inch.
Test runs revealed a machine that consumed coal at terrifying rates,
nearly double the pressure of conventional locomotives at the time. This required special materials and construction techniques.
The rebuilt machine limped through a handful of tests before being abandoned entirely due to persistent mechanical failures that made it utterly useless for regular service. In 1933, Italian state railways decided to transform a perfectly good Class 685 locomotive
and specialized knowledge that most railway workshops simply didn't possess. Then, during a test run in 1930, the boiler tubes and fittings were operating at the very limits of available materials technology. Testing began in 1930, and initial results seemed encouraging, making Fury one of the most technically advanced locomotives of its era. They could extract significantly more work from each pound of steam generated.
Proved hopelessly inadequate in the confined spaces of a locomotive. Engineers removed the reliable piston engine and installed a steam turbine in its place, leaving everything else completely unchanged. The locomotive still looked like a standard 2-6-2 wheel arrangement, but now it had turbine gearing where pistons once lived. The results were catastrophic. Performance plummeted to levels well below the original piston-driven locomotive. The turbine simply could not deliver power efficiently across the speed ranges that railway operation demanded. Maintaining speed on grades proved nearly impossible. The boiler, designed for a reciprocating engine's intermittent steam demand, within months, the turbine mechanism literally broke apart during testing. Metal fragments scattered through the machinery as stressed components gave way. They simply refitted the locomotive with a conventional piston engine in 1936 and pretended the whole turbine episode never happened. Italian engineers did not bother rebuilding the experiment. The failed conversion stood as proof that bolting new technology onto old designs rarely ends well. Ross Winans built his first camel locomotives for the Baltimore and Ohio Railroad starting in 1848, and from the beginning, crews knew something was terribly wrong. Winans wanted maximum weight over the driving wheels for better traction,
and served as a sobering reminder that technological ambition must be balanced with safety considerations. Number 6. The locomotive was later rebuilt with a conventional boiler and renamed. This incident shocked the railway industry and raised serious questions about the viability of ultra-high-pressure steam technology. Were unacceptable. The materials and engineering knowledge of the time were simply insufficient to safely operate boilers at these pressures. Fury was withdrawn from service immediately.
The fireman worked alone on a platform at the rear, completely exposed to weather and separated from the engineer by an entire roaring boiler.
The result was a machine that looked unlike any steam locomotive before it. The crew member in the fireman's position suffered fatal injuries from the escaping steam. Following a thorough investigation, railway authorities concluded that the risks associated with such extreme pressures developed one of the most unconventional steam locomotives ever built in Britain. The leader class was designed to combine the efficiency of steam power.
Despite these dangers, Winans built hundreds of camels, prioritizing fuel savings over human safety. The Pennsylvania Railroad's engineering department in the 1930s sketched designs for what would have been the most ambitious, articulated locomotive ever conceived. The locomotive would have exhausted its steam reserves within seconds of starting, leaving a £250,000 machine stranded on the main line. Pennsylvania Railroad engineers quietly shelved the proposal, recognizing that ambition had outpaced physics.
The leader featured a completely enclosed design with driving cabs at both ends, eliminating the need to turn the locomotive at the end of each journey. The boiler and machinery were housed in a central section, with the crew protected in comfortable, fully enclosed cabs. On paper,
3 of these 106-foot monsters were built by Baldwin Westinghouse to prove that steam could compete with diesel on premier passenger runs.
As speed increased, diesel fuel was injected, and the engine transitioned to diesel operation, with steam providing assistance.
Water from the condensing system followed the dust, turning coal residue into an abrasive slurry that destroyed electrical components. The locomotives could not complete a single journey from Washington to Cincinnati without suffering some kind of failure. After spending millions on development, the C&O operated their M1s for barely a year before giving up.
Number 5. The Kitson-Still locomotive. In the 1920s, engineers were exploring ways to combine the best features of steam and internal combustion engines. The complex chain-driven mechanism that transmitted power to the wheels proved troublesome, requiring frequent adjustment and repair. Reliability was poor.
Baldwin built the first triplex for the Erie Railroad in 1914, naming it the Matt H. Shea, after a beloved company engineer. The reality proved that some problems cannot be solved by simply adding more cylinders. The Matt H. Shea generated 160,000 pounds of tractive effort, more than any steam locomotive before or since. This massive force immediately created new problems. Couplers snapped, car frames twisted, drawbars pulled out of freight cars like corks from bottles.
The locomotive, delivered in 1925, was a massive articulated machine with separate engine units at each end and the boiler suspended between them. The railway industry concluded that specialized locomotives, whether pure steam or pure diesel, were more practical than attempting to combine both technologies in a single machine. Number 4. The the Biograt oil burning experiment for London transport in the 1920s.
Within months, the North British Locomotive Company quietly rebuilt the entire locomotive with conventional direct drive turbines, hoping to salvage something from the disaster.
The Fury, London Midland and Scottish Railway's Hypershore experiment in 1929. The London Midland and Scottish Railway embarked on an ambitious project to develop a Hypershore steam locomotive. These are the stories of 7 such machines. Number 7, that would set new standards for efficiency. The result was a locomotive initially numbered 6,399. The engineers behind Fury believed that by dramatically increasing boiler pressure,
while producing barely adequate power, mechanics spent more time repairing it than running it.
fans drove air through these condensers, cooling the exhaust steam and converting it back to water. In theory, this should have allowed almost indefinite operation without taking on water, where the challenging operating environment of the semi-arid Karoo region inspired unusual locomotive designs.
This made the T1 extraordinarily prone to wheel slip, violent wheel slip that occurred without warning at any speed. Engineers reported front drivers spinning wildly, while rear drivers gripped normally, sending shudders through the locomotive.
Operating departments found them unreliable and difficult to maintain with standard railway facilities. The specialized knowledge required to service these unusual machines was often not available at smaller depots. The ride quality was often poor, with vibration from the engine and rough suspension making passenger travel uncomfortable. The vertical boiler, while space efficient, was difficult to maintain and prone to steaming problems. Water capacity was limited, requiring frequent stops for refilling. Some experimental variants incorporated unusual features that proved impractical.
But the T1s concealed a fatal flaw that made them nearly uncontrollable. The divided drive arrangement placed 2 sets of driving wheels on a rigid frame, each powered by its own cylinders. Instead, it demonstrated everything wrong with late-era steam technology. The water tube boiler required specialized maintenance that most crews could not perform. Wheel slip damaged valve gear, which caused more slip. By 1948, the Pennsylvania Railroad had begun replacing their revolutionary T1s with diesel locomotives. Every single locomotive was scrapped. None were preserved.
Some locomotives had flaws so fundamental, trying new concepts and technologies in the pursuit of better performance.
Bearings failed. Generators overheated. The condensing system, essential for turbine efficiency,
but more commonly known as Fury. This machine was designed to operate at extremely high boiler pressure. Perhaps most critically, the leader's performance failed to justify its complexity and cost. By 1950, with British Railways already committed to desalination, continuing with the Leader project made little sense. Only 1 leader was completed, and it operated for barely a year before being permanently withdrawn in 1950. Tragedy occurred. A boiler tube failed catastrophically, releasing superheated steam at 900 pounds per square inch.
Railroad workers called these locomotives dangerous long before safety regulators existed. Engineers perched directly above the whirling side rods and main rods, with nothing but thin cab walls between them and disaster.
This design offered numerous advantages, including better working conditions for crews, reduced turnaround times, and improved visibility. Construction of the first leader began in 1948, and it was completed in 1949. However, problems emerged as soon as testing began.
Most remarkably, the system could have run on renewable biogas, creating a carbon-neutral steam locomotive in 1960. Engineers now recognize this as the greatest missed opportunity in locomotive history. If railroads had embraced the design, they might have achieved environmental compliance decades before regulations forced expensive retrofits.